Okay, so I just want you to tell me if the audio is like proper or is the volume correct, or do you need it? Do you want it to be a little more? Do you want me to
Clear,
be
sir.
louder? It's clear, right? Okay.
Clear, sir. Audio is clear.
Okay, so we'll just wait for like 2 minutes. We'll start at 6:05. So see the plan. The plan is going to be as follows. I am hoping that most of you wouldn't have watched the lectures, right? And I also recall that many of you were not able to join last week's session because of another meeting that was scheduled during that time. So I'll quickly do a recap of week 5's content and then we'll move on to week 6. Okay, and so we'll have one more session. So we'll have 3 sessions this week. This will be one. Wednesday, we'll try to have one session for the programming part. We'll try to explore this NumPy matplotlib in little more detail, or like fix the problems that seem to be there, some difficulties with respect to the programming part. And then Saturday will be like more of a, again, coding plus theory kind of session. Okay, so shall we start then?
Yes, sir.
Okay.
Yes, sir.
Yeah. So again, so some. Yeah. So some of you, for some of you, this will be repetition, but I'll try to go fast. Okay.
Hello, sir.
Yeah.
Sir, sorry for interrupting you, but I am having problem with understanding multi-class and multi-level, and with an example, if you can explain that.
Yeah, we'll come to that. Maybe not right now because I have an agenda already set for the meeting. We'll have, as I said, there'll be 3 sessions, right? So in one of these 3, we'll surely tackle this. You want to know the difference between multi-class and multi-level, right?
And when they are together, how can we say that? With an example, if it is possible.
Yeah. Okay. We will take this up, but not right away. Okay. Not right now. Okay. So yeah, I mean, as and when it comes, if some of you have any doubts, you can I'll note it down here and then we can address it later. Okay, so week 1 was just an introduction. Weeks 2 and 3 was about regression, and we saw linear and polynomial regression. And then weeks 3 and 4, or rather week 4 was about classification. We started off with extending this linear regression to classification, which is what is least square classification. And then that was one model, and then we moved on to perceptron, right? And both of them, if you recall, they ended up learning some kind of a decision boundary like this, right? And the decision boundary was of this form, right? W transpose x equal to 0, right? So that was the decision boundary that both perceptron and least square classification, both of them ended up learning. So one theme which is common among all these models is linearity, right? So what do I mean by linearity? I mean this expression, right? W transpose x. So the output, right, is linear in the features and the weights. In this case, that's what it means. So this is going to stick with you till the end of the course, right? W transpose x is one expression that you will see in various disguises, but it will never leave you for the 12 weeks, right? So it's important that we get used to this expression. So in regression, y was equal to w transpose x directly, right? In polynomial regression, we just transformed this x into phi of x and then did w transpose phi of x. But essentially, that is also linear only, right? In the transformed space, it is linear. In least square classification, what we did was we again learned this w's using w transpose x, but we say that, once you learn it, then say whenever w transpose x is greater than 0, we call it class 1, and it is less than 0, we call it class -1 or 0, right? So that was least square classification. In perceptron also we do the same thing. Only difference is that perceptron has a different update rule compared to least square classification. Okay, so the other common thing is that all of these we learned using gradient descent. The weights were learned using gradient descent. So the next step in the series is again another classification algorithm, but this is called logistic regression. Okay, so there is a slight push from the model's side towards nonlinearity. Okay, so I'll tell you what it means. Don't worry too much about this term called activation function now. So a lot of week 5 is about trying to understand this sigmoid function, right? So 1 by 1 plus e power minus z. Okay, so how does it look? It's more important to understand the graph than understanding this formula. So this formula is, you can keep it aside for now, but the graph is something that you need to understand. It is the sigmoid function takes a real number as input. Okay, it takes some real number as input and it squishes it between 0 and 1. Okay, so I'll just, for added emphasis, I'll just write this down so that we don't forget. So this sigma of z takes a real number as input and outputs a number between 0 and 1. Okay, so can someone tell me why this is useful? Why should it be between 0 and 1?
Looks like a probability.
Right, because we want a probability, right? It looks like a probability, that is right, and we are moving towards that. So yeah, now that we understand or we know what this function is doing, so as I said, just remember what this function looks like, what the graph looks like. Takes real number as input and pushes it between 0 and 1. Okay, so now what is this logistic regression model actually trying to do? It takes some feature vector as input, okay, and then it outputs a probability. What probability does it output? It outputs the probability of seeing this class 1 given this feature vector x, right? So it outputs a conditional probability, or rather it outputs a number between 0 and 1 and we interpret it as a probability. So is this point clear to everyone? Because this is the crux of the model.
Yeah, so I mean, maybe I don't know if it is too mathematically complex, but is it really probability though? What it is generating?
Yeah,
the sigmoid function.
That's a good point. So it is generating some number between 0 and 1. Okay, and we are interpreting or modeling it as a conditional probability, right? So this is where we come in and say, okay, hey, this is the model that I choose. This is how I represent my this is how I want to model my probability, right? And I call it sigma of w transpose x. Okay, so this is a modeling assumption.
So I just have one doubt. So basically, in the previous week, we saw there was a step function like 0 and 1. So in this case, what we are doing is we are trying to create a curve out there between 0 and 1. And that's why we are using the sigmoid function to see, because there it was very, very distinct. You either get class 0 or class 1. So right. Here we are getting values between 0 and 1.
Yeah. So see, there is a reason we are doing that. So let's take this case of in least square classification. What happened was, So we have this, once you learn this decision boundary, then you say that y equal to 1 if w transpose x is greater than 0, and y equal to say 0 or -1 depending on what your convention is. Say I'll say y equal to 0 if w transpose x is less than or equal to 0, right? So
Right.
this is what least square classification does. This is what perceptron does. Okay, again, this is what stage of the process? This is inference, right? Once you have learned a w, you are trying to infer the class from your model, right? So the model is not actually returning you anything. It's only returning you some scalar value called w transpose x, and you choose to interpret it this way, right? So there is some interpretation that's happening. Okay, so this is what LSC does. This is what perceptron does. But there is what logistic regression is doing is it's not trying to do a very hard interpretation. It's saying, okay, see, at the end of the day, everything is probabilistic in nature, right? There's a lot of uncertainty in my data. So I am not going to tell you at the outset whether it is class 0 or class 1. What I'll give you is a probability. It's a probability measure. I'll tell you that, this point, this red point here has, a probability of 0.7 of being class 1. Whereas this red point out there has a much greater probability of being class 1. That is what it's trying to do. Basically, geometrically, if you think about it, for points that are close to the decision boundary, logistic regression model will give you a low probability. And as you move away and away, as you become more confident, it will give you a probability that is closer and closer to 1.
Got it, sir.
Okay, so we'll see why. I mean, this is geometrically, but we'll see how the algebra supports this. We'll come to that. But what we need to understand is that you input an x and you get a conditional probability. And we choose to model that as follows, right? So, okay, inside what's happening, you take x, you do w transpose x. Step 1 is common to all the models we have seen so far. The only new addition is step 2, where you do a sigmoid of this w transpose x so that it becomes a number between 0 and 1. Okay, so p of y equal to 1 given x is sigma of w transpose x. So far what we have done is we have specified the model. Okay, once we have specified the model, we need to learn the weights. Okay, so that's the next step. How do you learn the weights? If you recall from statistics 2 course, we have done this. We have learned this process called maximum likelihood estimation, right? So basically, this is what? This is parameter estimation. Okay, so you are given some probability distribution, right? And you are given some data. Now, how do you estimate the parameters that best fit this data? So this is the problem that we are trying to solve, and there are several ways to do it. One of the ways is MLE, or maximum likelihood estimation. Does everyone remember some parts of MLE?
Yes, sir. Yes.
Okay.
Yes, sir.
All right. So yeah, so our parameters here will be W. Okay, so parameters here will be W, but before we go there, this P of y equal to 1 given x, right? We are saying that this is sigma of W transpose x. That's what we are saying. So can someone tell me what distribution, okay, spelling wrong. Can you tell me what distribution P is? I mean, what is the distribution corresponding to P? What is it?
Bernoulli?
Correct. Yeah, that is right. What distribution is P? It is a Bernoulli distribution, right? So it is Bernoulli with where I can call it Bernoulli of P, where this P will be sigma of W transpose X. Okay, is that clear to everyone? This is a Bernoulli distribution. Basically, y equal to 1 given X, right? So I can take only two values, either 0 or 1, depending on, so it's a binary classification setup. So probability of success is P, probability of failure is 1 minus P. And the interesting thing is that it depends on the data point or feature vector X. Okay, so yeah, once that is set, we can go ahead with maximum likelihood estimation. Okay, so one of the important assumptions that we'll make here is that all your data points are independent and identically distributed. Okay, so this is the IID assumption. I'm sure you would have studied this in stats 2. If not, you can, I'll pause and explain this, but otherwise I'll just move on. So you assume that they all come from the same distribution, which is this particular distribution. So that is what we mean by identically distributed. And we also assume that they are independent, right? So moment we assume that they are all drawn independently, the probability of seeing this entire data set is nothing but the product of probabilities of seeing individual points. Okay, so that is called likelihood, right? So how likelihood is nothing but how likely is it that I observe this data set coming from this distribution P of y given X. Okay, so I'll just repeat that. So this is one point, and here what we are doing is we are doing MLE, where we are computing the likelihood, which is nothing but how likely is it to observe data set D generated from P of y given X. So that is what we are trying to maximize, right? So we want to maximize the probability of or the likelihood of this data coming from this distribution. Okay, I hope this step is clear.
Yes, sir.
Okay, so once you have the likelihood, it is always, since we are working with probabilities, if you multiply the probabilities of n numbers, where each of them is between 0 and 1, you will end up working with some very small numbers. So it's always easier to work with log of probability. So we take the log of likelihood. Okay, that ends up, so that will give you L of W, small L of W. And what I have here is the negative log of likelihood. Okay, so maybe I went too fast there. So what I'm saying is you have likelihood, and then you move on to log of L of W, right? I call this, say, small L of W. And if I want to maximize the log of, if I want to maximize likelihood, it's the same as maximizing log of likelihood, which is the same as minimizing the negative log of likelihood. Okay, so I want to maximize likelihood, which is the same as minimizing the negative log of likelihood, which is what I've written here.
So here I got a little confused. So why are we trying to maximize the likelihood? Wouldn't that be maximizing the loss itself?
Good point. So we are not, so this is not the loss, right? So the loss comes a little bit later. So currently when we are defining the likelihood, we don't have the concept of loss as of now, right?
Okay, this is just probability.
Yeah, this is just the product of many probabilities, which is the likelihood. I am still in the probabilistic or statistical domain, right? I'm trying to maximize the chances of this data set coming from this distribution. So
we are making an estimate of W basically.
Yeah, we are trying to make an estimate of W. when we try to minimize the negative log likelihood, right, that becomes the loss. So we call this the loss.
Okay.
Okay, so there is a reason this is the loss. So I'll, there is a good reason this is called the loss.
So once you know your weight vector, you can calculate the loss. Until you don't know your y vector, w vector, you can't compute the loss.
Right.
Yeah.
But it's yeah, but there is a good reason, right? I'll tell you what the reason is. So this is the negative log of likelihood, and I say that this is right. We are moving from I equal to 1 to n, right? So there are n training examples. So this is sum over I equal to 1 to n minus yi. This is the label of the ith example, and this is log of sigma of w transpose x I, okay, minus 1 minus yi log of 1 minus sigma of w transpose xi. Okay, so this is the expression. Now what I'll do is I'll just slightly change this expression. Okay, I'll rewrite it in a way that is easier to understand. So the sum still goes from I equal to 1 to n, minus yi remains the same, but here I'll write I'll write y hat of I, and here I'll write 1 minus y hat of I. Okay, so now focus on, say, one example, right? And I'll call this the loss. So just focus on one example. Let's say that training example has label 1, right? So if the training example has label 1, what do you think this expression will become? Just forget the summation. Now just look at this expression here. If the label is 1,
one of them will be
only
0.
The
right?
first
One
part
minus
will
one.
remain, sir.
Yeah.
It will be log 1.
right?
Yeah.
So this first part will remain, right? So it will be yi is 1. So I'm just going to.
Right. Yeah.
So it will just be log of y hat, right?
Yeah.
So
Y hat.
right. So let's interpret this thing. Now I'll just write this down. If my true label is 1, then yi is 1, right? So if my true label is 1, then yi is 1. That's the first statement. Now what is loss? Loss is I want to penalize my model if it predicts something other than 1, right? So I'll just add this second point also. What is yi? It is the probability that the label is 1 given the data point. Okay, is the second point clear?
Yeah.
Okay, so this is nothing but sigma of w transpose xi. So this is nothing but the probability that p of y equal to 1 given x. So this is the probability that the label is 1 given the data point. Now, what is a good loss function? A good loss function should add some penalty if, or it should penalize me if my prediction is way off the true label, right? So if y hat I is equal to 1 or yi hat equal to 1, then the loss is 0. Do you see that? If I make the correct prediction of yi hat equal to 1, loss is 0. Okay. Now what happens if I make the wrong prediction? If I say yi hat equal to, maybe not equal to 0, let's take yi hat to be a very small number, right? So let's say I make this. Okay, so what will be the answer? Assume I take log to the base 10.
Minus 3 or 3 minus 3.
This will be 3, right?
Yeah, minus or minus 3. Yeah.
Okay, so now do you see what's happening? If I predict the wrong label, then what's going to happen? My loss is going to go up. Okay, so this is, do you see why this whole thing is a loss function now?
Yeah.
Okay, so this is important, right? This crazy expression that you see here is actually very intuitive. Okay, let's now do the other case. If my true label is 0, then YA is 0. Okay, so this term will vanish. The first term will vanish. So what will remain is, this is what will remain. Okay. So let's say, so if yi hat is near 0, then I have no problem. The loss is going to be 0. On the other hand, if yi, yeah.
So why not that 1 minus yi?
That is because this, if yi is 0, this term will vanish, but this term will remain, right?
Yeah, the entire term, yeah.
Yeah, so it will be, oh, okay. You're asking why not? So this YA is 0, right? So
yeah.
that 1 minus YA will become just 1.
Okay. Sorry. Yeah, got it. Sir.
Okay, so this will be just log of 1 minus YA hat. And if YA hat is close to 1, let's say 0.999, right? You will get something like this again. So loss will again be high. Okay, so this loss is what is called negative log likelihood, or it's also called binary cross-entropy. Okay, we don't need to worry too much about why it's called cross-entropy or why it's called binary cross-entropy, but I hope this negative log likelihood makes sense.
Yes, sir.
Okay, so this is why it's a loss function. So minimize the loss.
Plus, it also looks very much like a convex function, right? You have this lambda x1 minus plus 1 minus lambda x2 kind of a model.
Right. True.
It's like a PLNP, right? Entropy, right? Physics. So it has that form.
Yeah.
And it's like an inverted U. So it is pretty logical, smooth function.
Right.
Yeah.
So basically, by doing this maximum likelihood, we are also optimizing it if we do the whole procedure, like different partial differentiated. And
correct. Yeah. So we could either look at it as, so there are two ways to look at it, right? I could either look at it as, parameter estimation using MLE. I mean, you could just think about it that way, or you could, other interpretation is you optimize a loss function, say using gradient descent or whatever, right? So both of them are the same actually. I mean, you started off with this,
clear,
but you end up doing this, right? So that
Emily,
is, sorry.
Emily gives the closed form solution.
Right. Yeah. So if you differentiate the whole thing and set it to 0, we'll get the closed form.
Yeah, it will be, I think, for binomial, to estimate the P, it will be sigma xi by n, like that, or like that, when you do the MLE method.
Okay. I'm not sure about it though. See, because I think I'm not sure if we have discussed the closed form for this logistic regression. We have only stuck to the gradient descent based iterative solution. So, but that's an interesting point. I'll do some. Either one of you can do this digging up, or I can do it also. But I've never seen the closed form solution for this setup, right? I only seen the gradient descent approach, but maybe we can discuss that later. But please remind me. I'll maybe add this to.
So why I have one doubt. Why do you call it gradient descent approach? Because gradient descent works on convex functions. So log function. How will it be convex?
Good point. So I'll get back to you on this also, right? This is also a bit unclear now. I need to study this part a little bit more and get back to you. See, even if your function is not convex, we will still stick to gradient descent, right? So gradient descent is, I get your point. So if it is convex, then if you use gradient descent, then you are in some sense guaranteed to converge to the
This is
global.
this is convex though, isn't it? Because it has the form of lambda
Right.
x1
Yeah,
plus
but
1 minus lambda.
yeah, but again, I don't want to commit here. I'll pose these as questions. Okay, I'll get back to you on this in one of these two sessions, right? So is the negative log likelihood convex? And the second thing is, do we have a closed form solution for the logistic regression setup? Okay. For now, let's set it aside. But these are good questions and they need to be addressed. But right now, I am not in a position to address them.
It starts to weird a homework on a binomial distribution. You take the form, p to the power x, 1 minus p to the power n minus x. You do the log likelihood and then find the MLE. So I remember doing an exercise.
Okay.
Yeah.
Okay. That would be great if you can point.
I sent you a link with from Penn State. There is actually a derivation on binomial MLE for binomial distribution.
Okay.
Yeah.
Yeah, but these three problems are open. Okay, this first one is I can address it, but second and third I need to do some research on my own before I can get back to you.
Yeah. So if you generate random numbers like a 0 and 1, right? So the binomial will be basically like a p, right? So it will be basically sigma xi by n, right? It's very logical, right? The average that will converge to the probability. So that's why that sigma xi by n should be the MLE, when we derive it. So anyway, you'll see the link.
Yeah, sure.
Yeah.
Okay, so yeah, so once we have assumed that we have trained the model and now it's time for inference, right? So how does the decision boundary look? This is one question we need to know or the answer to. So if you look at the geometry of the decision boundary for a logistic regression model, it will be, so how do we arrive at that? So something like this. You look at the probability output by the model, right? And if it is greater than some threshold, we call it label 1, class 1. If not, we call it class 0. Okay, so this is how inference works in logistic regression. Now, when is this greater than 0.5? So this is greater than 0.5 when the sigmoid value is greater than 0.5 because the probability is the sigmoid. When will this be greater than 0.5? If you look at the graph to the right. Okay, so whenever your x, the z value, whatever is inside the bracket, right, is the z value. Whenever that is greater than 0, the function will be greater than 0.5. Okay, so in conclusion, what we can see is that you will predict a data point to be class 1 if W transpose X is greater than 0. You will predict it to be 0, class 0, if it is less than or equal to 0. Okay, so what is the decision boundary in this case then?
W transpose X equal to 0.
Yeah, right. So it is a linear decision boundary. So it's we are back to linearity. So this is, in some sense, if you just look at the decision boundary, you cannot say whether it's a perceptron or it's a least square classification model or it's a logistic regression model. If you are just given the decision boundary, there is no way you can find it out. Okay, so but still there are some advantages of LR over all these other models, and that advantage is in the probabilistic way in which it looks at things.
Sir, but W transpose X is passed on to the sigmoid function. So how is the hyperplane linear?
See, the what is the hyperplane? The hyperplane is a divider, right? It divides the two classes, right? So you are essentially asking for what values of x, W transpose x is greater than 0, right? How do you decide how do you come up with the decision boundary? You look at every point in Rn and you ask this question, is W transpose x greater than 0 or less than or equal to 0? And depending on that, you color that particular point, right? And whatever is the boundary that you get, that is the decision boundary, right? So the set of points for which this is greater than 0 is one half plane, right? It's a typical half plane. Is that convincing? Can you rephrase your question?
Is it the composition of the sigmoid function is linear?
Okay, so I'll see. These are the following steps, right? So see, how do you find the decision boundary? Assume that this line is not there. Okay, this line is not there. So the task is, what is the decision boundary, right? Now we have learned a model, and that what is that model? That model is this is the model, right? So now I want to answer this question: what is the decision boundary? So what I'll do is I will pick up one point at a time from this XY plane. Okay, so assume that they don't have any colors. They're all just some colorless points, right? I'll pick up, say, this 7, 4, and then 5, 3. So each point I'll get hold of each such point. I'll pass it through this model. It will give me some probability. Correct? So if that probability is greater than 0.5, I will color that model as blue. Sorry, I'll color that point as blue. If not, I'll color it as red. Do you get what we are trying to do so far?
Yes, sir.
Using the threshold, you'll basically put them into two classes, either blue or red or whatever, right?
Yeah. So I will. What we are doing is, we are going to color the entire plane into blue or red. Every point is going to get one color, which is basically blue or red, depending on the outcome of this probability. Okay. So now, if you notice, what are those points for which you will get this blue color? All those points for which W transpose X is greater than 0 will get blue color, right? That's because of the property of the sigmoid function, right? Anything that is positive will return a value of 0.5 and above, and anything that is negative will give you a value of 0.5 and below.
Okay, sir. Got it.
Right. So now, just for completeness sake, less than or equal to 0, I'll color them as red. So forget all these fellows. So this W transpose X equal to 0 line is basically this something which is colorless, right? I mean, for the sake of our argument, assume that I color those that are less than 0 as red, greater than 0 as blue. So you will finally have one line which is W transpose X equal to 0, which is no, you can't determine the color of that line, right? So this is the decision boundary, and everything that falls to one side of the decision boundary is going to be blue. Everything that falls to the other side is going to be red. Okay, this is how you compute the decision boundary. And since this is linear, I say that the decision boundary is linear.
Yeah, got it.
Clear, sir.
Okay. Yeah.
Thank you.
Yeah. So,
sir, what
yeah.
if the probability is 0.5, we are giving it as W transpose X equal to 0. If the threshold is not with some other value, what will be the case?
Good point. So if the threshold is some other value, what will happen? You're asking.
Yes, sir.
Okay. So this is I won't answer this now. This is a quiz question that was asked in last term. So I request you to, I hope you have access to the quiz papers.
Quiz
Right?
2.
Yeah, quiz 2. So you can go take a look at that question and you try answering that. If you're not able to get the answer, you please start a thread on discourse.
Okay, sir.
Okay, so I'll just this is a good question. So maybe all of you can try to attempt this.
So it's actually, kind of, if the distribution is not symmetric, it's not around actual P is not 0.5. It intuitively says that P hat cutoff should be lower. So depending on your cutoff, the original, the algorithm obviously will have a precision recall. So you want to create a decision boundary which maximizes the precision recall. So I think the choice of P hat or the decision boundary is going to be critical for real life applications, right? So
true, yeah. So there is a question on this also in quiz 2. You can take a look at that, right? So this is a very good question, and this is a very good point. These are the choice of is relevant.
In the video, it was mentioned that it is an hyperparameter which we can tune.
Yeah, true. That is also true. So once you learn the model, as long as you, or until you learn the model, this threshold doesn't enter. But at inference, right? At inference time, threshold is very important. So yeah. So these are 2 questions that you can try to answer. What is the decision boundary for a logistic regression model if the threshold is t, right? Some t. T obviously should be between 0 and 1. Okay, so this is one question you can ask yourself. The second question is, how do we choose t, right? So when should t be high, when should t be low? So these are 2 questions that I don't want to answer now, but please go back to quiz 2 paper and find out the relevant questions which will give you the answer to this.
So can I cite a real life example? So maybe that will help. So let's say we are building a model to classify fraudulent transaction versus not. Let's say we are taking Paytm data. We are doing consulting work. Out of 100 transactions, only let's say 1 EPA transaction is fraudulent, 99 are not fraudulent. So we can build it using a logistic model. We'll get a P hat. Now, depending on the cutoff, my model would have a precision recall.
True.
Right? So in that case, there is also customer impact. Like if I don't set it properly, I'll create a lot of false positives. So that means a lot of good customers will get their transaction declined for a credit card company or API company, right? So these are all real life implications. So there is a cost to the false positive as well as true positive. It's not symmetric in real life.
Right.
So that is where these kind of decisions are actually extremely important.
Yeah. Another example, which we asked in quiz 2 was metal detectors at airports, right? So you need to be very careful what you detect. So it's okay if you have a lot of false positives. So even if someone is not carrying something sensitive, you can flag that person as positive, right? But it's very dangerous if you let some of them through, right? So false positives are good, but false negatives are not so good. Okay, so that is one example which is there in. Yeah, so I leave this as.
Sir, I have a question. I have a doubt here, sir.
Yeah.
So in this, we are assuming that the distribution is Bernoulli, right?
In this, yeah, we are assuming that the distribution is Bernoulli.
So sir, then how can we take example of tail events, which are, like 1 in 100 type of case? Because that distribution will be absolutely different. It is not going to be Bernoulli.
Why not? It's a yes or a no. So why will it not be a Bernoulli?
See, this Bernoulli is not like, it's not like if you compare it to a coin toss, it's not a unbiased coin toss, right? It's a biased coin. So my probability of success can be say 1% or 99%, right? It is Bernoulli in that sense, but it can be a very biased outcome. I can also model a very biased situation, right?
Okay.
So basically the threshold is other than 0.5 when the data is unbalanced, right, sir?
Typically, if you have class imbalance, then yeah, you need to be, but it's not just about class imbalance, but also about
Cost function.
how you want how confident you want your model to be. So see, for example, there are applications where you want to be really sure before you predict something as class 1. For example, this metal detector case, right? I want to be or let's say medical diagnosis, right? So before you say someone has cancer, maybe you want to be really sure, right? You look at the record of a patient and you run a logistic regression model for, say, cancer detection, right? And I can think of two scenarios. One where the doctor or whoever it is, right, wants to be really sure before going ahead with a model, right? So there I'll tweak my threshold and make sure that unless the model is like really say 99% accurate, right, or confident that that particular example is a true positive, it won't output the label as true.
So that is where we'll have a very high threshold, right, sir?
That is where we'll have a very high threshold.
Yeah.
On the other hand, for let's say a metal detector kind of an application where I don't want to miss out on any positives, so I have a very low threshold. So just even if I am going to call out a lot of examples as positive, I don't mind, right? So I don't want to let any of the bad guys through my metal detector.
Yeah, yes, sir.
Sir, I have one point here.
Yeah, please.
Yeah. So for the second question, where the choosing the threshold, I have one idea. So to choose the threshold, let's see the first the sigmoid function. So if I see carefully the sigmoid function, then it's changed the concavity 2 times. And the point of the changing concavity is the threshold, I can say, if I see the function. So first, before the threshold, concavity of the up, and just after the threshold, concavity is the down. So if I have some data of the table, and I can do one thing, I can find the consecutive tangent at every point for the every data, and where I will see that. So in the all cases from the minus infinity to infinity, the tangent is always positive, but at the threshold it is the maximum tangent. So what will happen, when the concavity is going minus infinity to threshold, the tangent value is going up, and after threshold tangent value is going down. So I can say that after taking the tangent, so wherever that concavity is changed, that means the tangent value is going high to low. I can say that the highest point is the threshold. That is the idea I thought.
Okay, you mean by looking at this graph, you're saying?
Correct. So
right.
Since we have a data, obviously we will have the data. So I can do consecutive data and its output level. I can take its x and y value, and I can take the tangent at every point. So before threshold, the tangent value will be the something, and just after threshold, tangent value will be the something. But at the threshold point, the tangent value will be go maximum. So if I plot that particular tangent value, then moment I see that where the maximum occurs, that is the threshold point. Technically and theoretically, I can say. Mathematically.
Okay. All right, but see this typically, right? This threshold is this particular threshold is chosen more from an application standpoint, right? So a lot depend.
Yes,
yeah.
sir. So I'm also getting that the point from the that idea of the tangent value from the point itself, the point as provided to us. Because that I will train some data on the machine learning. No? So they must give some features and some level. So if I take that features and level as the x and y, and I make the tangent somehow, if it is some word, then I will convert in the number, or somehow if I convert in the number, then I can say that after tangent way, I can find the actual threshold mathematically.
Okay,
Yeah.
okay.
So there is one more point I'd like to add. I mean, what Kumar is saying is correct. Assuming that type 1 and type 2 errors are given equal weightage. Because what if your true positive or false negative have different weightage or cost functions? Then it is not going to be true. Because theoretically, your decision boundary will only tell you the classification. Where to do the threshold has to depend on your cost function.
Okay, but see, cost function is fixed here, right? I mean, for the simple example, we are not changing it much. We are just going with the negative log likely, right? So,
no, I mean, to talk about in a real life application where you're going to apply the cost of making a false positive mistake or a
true,
false
yeah,
negative,
yeah,
right?
yeah.
So let's say the cancer example you gave, right? So misclassification doesn't have a symmetric cost or loss, basically, right? Because misclassifying a good healthy patient as having cancer is more dangerous than letting a cancer patient not diagnosed as having cancer, because then in that worst case, so that is why in real life the cost functions are not symmetric. So even if theoretically you can come up with a the point of contraflexure where you should do it, but real life it is actually you have to consider recall and precision and then optimize the hyperparameter based on the application. So it's not a theoretical decision, it also has to consider the cost function. So what Kumar said is correct, assuming the cost functions are same for both sides, misclassification.
Right.
I have a one point here, sir. Actually, so before telling this point, I have a one question, and I don't need answer now. Just I want to point out my question in the machine learning practice. Means when I was thinking. So the problem is, can I ask that problem, sir?
Yeah, but I will. Can we move it to the end, because
okay, sir. So that problem actually I was learning regarding the sigmoid and the linear regression to the logistic regression. So I was thinking I was solving some problem. I was trying to do something, and I get so many problems. I thought that I will add this one. So okay, I will add in the last.
Yeah, sure.
Okay.
Right. So this is more like what we are doing here is more like a revision of week 5, and we haven't even started week 6. So I'll just move on from here. Okay. So we know what the decision boundary looks like, and we have some data matrix, right? So our feature matrix, n data points, m features, and a label vector with n data points and 1 or 0 being the label. So this is something I want all of us to understand. What happens? So this gradient we keep subtracting, right? In gradient descent, w equal to w minus alpha times the gradient. So what is really happening is something that we need to understand. So for gradient descent, this is how the gradient will look like. Okay, so if you want the detailed derivation, you can go refer to these slides, but it's fairly a simple one, right? So if you remember, linear regression also had something similar. X transpose into xw minus y was for linear regression. For logistic regression, the only change is that it's sigma of xw minus y.
Yes, sir.
Right. So this sigma of xw is what? It's a probability, right? It's a vector of probabilities. So I can write this as y probability minus y. This y probability minus y is, in some sense, I call it an error vector, right? If you remember, we were discussing this part. If y probability is 1 and y is also 1, then the error is 0. On the other hand, if y probability is 0 and y is 1, then the error is minus 1, right? So this can be interpreted as an error vector for the n data points, which can in turn be expressed as this. So this is nothing but a linear combination of all the examples in your set, I equal to 1 to n. You are multiplying each example with the error corresponding to it. So is this form clear to everyone? This is a very nice expression. It will help us understand what gradient descent is actually doing. Is there anyone who is having problems with this particular form of the gradient?
Small example, if you can give, sir, it would be really
okay, so
sir, in the previous slide, you after X transpose, you had XW minus Y. So that's essentially error. You just substituted that.
Yeah,
that's all. Yeah.
So example, what example will I give? So, okay, we'll go to, we'll go to the next slide where things might become slightly clear what we are doing. Okay, so there are examples coming up. So for now, just trust me that the gradient of the loss with respect to the weights is, after doing all the math, it comes down to this sigma xi ei, where ei is the error in predicting the ith training example and xi is the ith training example. Okay, assuming that you are okay with this expression, this is just repetition of what I said. Let's see what happens to a single example, right? So the summation will go away. So x will be just some feature vector and this will be the error, right? So if you notice the gradient, right? The gradient, two things are important to find the gradient. One is the actual data point and the other is the error in prediction. Okay, so these two are very important, right? So when you look at a single training example and the effect of the gradient corresponding to that, two things matter. One is the actual data point and the other is the error in prediction. So here is one example of what's happening. Assume that this is your weight vector and this is your data point x. Okay, one is the dummy feature and -3 is the bias term. So your weight is 2, 3, this red color vector, right? It is pointing in the direction 2, 3. And your data point x, it's pointing in the direction -3, 2. Or rather, it's at the point -3, 2. Is this picture of the logistic regression model, is this clear what we are doing here?
Yes, clear, sir.
Okay,
Yes.
right. So y equal to 1 is your actual label. Okay, and currently everything to the left bottom of this line is predicted as class 0. Right. So this blue color point is actually misclassified now. Its true label is 1, but my prediction is that it's class 0 because it's 0.04, right? If you use a threshold of 0.5, I will predict it as class 0. So what I'm going to do is I'm going to apply this descent update rule, right? W equal to W minus X times Y probability minus Y. Okay, so this is the same as adding 0.96 into X. Okay, I'm roughly, it's like adding W equal to W plus X. Okay, W plus X. So geometrically, what does that mean? I end up with a new vector W new, okay, which is like this. So what has happened to this point X now? Can someone tell me what has changed in the model after this single update rule?
So the decision boundary is
The
coming
decision
closer.
boundary.
Yeah.
Okay, so the decision boundary has changed to this orange color line. So
Yeah.
as a result of that, what has happened?
The previously misclassified point is now classified properly.
Right. So this blue color point is now classified correctly, right? Its probability is 0.99.
Very similar to perceptron.
Yeah, it's very similar to perceptron. In fact, the update rule, if you notice, is more or less the same. Only thing is that in perceptron, this term would be 1, whereas here we have something slightly more subtle. It is Y probability minus Y.
Right.
So the in case of perceptron, it's like a horizontal line, a vertical line, and a horizontal line. Whereas in case of logit, it's like kind of smooth. It's not this like abrupt change. So that's the separator. So that's the only difference.
Right.
Yeah.
Okay. So this is what one update of. So this is basically what stochastic gradient descent, right? That's what I have done here. I have done one training example. I have computed the gradient and I have updated the weight. So this is some intuition as to why gradient descent works, right? Or rather, what happens really when you update the weights? Something like this is happening. Okay, so now let's take one more example where the point is classified correctly, right? So the blue color point here, the probability by the current logistic regression model is already pretty good. It's 0.99. Okay, so now if you notice, if you try to update the weights now, the error in prediction is very small, right? It's 0.01. So the new vector is going to be more or less the same, right? There is not much change in the weight vector. So your decision boundary remains practically still. So from this, we see that LR logistic regression is like much better in handling outliers compared to other models. Okay, again, this is something we need to make a note of. This is some animation that shows how logistic regression works using SGD for say 40 epochs, right? 40 or 50 epochs. Yeah, so that is.
So because probability is bounded, right? So even the outliers, whatever, right, has a probability of 0.99. So
True,
it will not
true,
impact
yeah.
at all, right? So
yeah. So that is what this slide is about. So
does this also have the same assumption of linearly separable data points for it to work?
True. So here also the linearity comes in, right? Because finally the decision boundary that you have is linear. Okay, so
right,
you have to, if you wanted to work on data that is non-linear in nature, non-linearly separable or linearly non-separable, right? Then you'll have to do the same polynomial transformation, and then you can learn the whole thing. Okay, so so these three models are very similar, right? That's the final point I want to make. All these classification models have pretty much the same form. Only thing is that this error term varies from one model to other. In perceptron, it's like -1 or +1, whereas in least square classification, this can be huge, right?
So it is the top one should be Y predict and the last one should be Y prob.
Yeah, I interchanged the things. Yeah, you're right. So this should be Y predict, right? So this is Y probability, right? So that is till week 5. That's what we have till week 5.
Sir, I think I can answer that question of convexity from the loss function derivative.
Okay, please go on.
So if you can show me the derivative. So one of the definition of convexity is that if the second derivative exists, if it is positive definite, you have convex function. So if you look at the first derivative, you already calculated for the gradient descent.
Gradient, right.
Yeah, so if you can look at that expression, I think we can differentiate this pretty easily and see that it is positive.
Positive definite, this one.
Yes.
Okay.
This is 1 by 1 plus something. So that is a square term coming there. And there will be an X transpose X in the numerator.
Okay. So this I'll probably take your cue and we'll work on this in discourse. Okay. So,
sir, besides sigmoid, aren't there any more functions which like take the data and map it between 0 and 1?
Not between 0 and 1 that I know of, but there are few more functions that we'll be studying in week 12. So for example, there is one function called tan h.
Okay. Yeah, sir, but that is not 0 and 1, right?
That is not 0 and 1, right. But typically they are all some kind of nonlinear functions. So they'll be used in a different context, but I am not aware of any other function that maps between 0 and 1, or at least something that is used in machine learning. I am not aware of.
But this tan h is like the tan.
Hyperbolic tangent, right? That one.
Okay.
So like this sigmoid kind of came out of nowhere. Like,
good point. That is also something I'll have to clarify. So between 0 and 1. So is there, actually there is, we can provide a probabilistic interpretation for why we use sigmoid, which we will come to in week 7. Okay. So in fact, if you are, there is a probabilistic interpretation for linear regression also. Okay. So I can ask one question for linear regression. Why do we have this loss function which says y minus, w transpose x? Why do I have that kind of a loss function? It's intuitively clear, right? I mean, you want that w transpose x to be close to y, so you want sum of squared errors. That is one way of looking at it. But there is actually a different motivation for linear regression, which completely gets rid of the loss function. It kind of loss function naturally comes about. So perhaps I'll discuss that in the next session. Now we don't have the time, or it may not be appropriate now. But I have noted down these questions. Okay, I'll get back to you.
So please post them in Discourse to like as a post.
Yeah, sure. Okay, so we begin week 6. So what we have been looking at so far, right? Logistic regression is a kind of discriminative model. Okay, so when we say discriminative, what we mean is we try to model this conditional probability of the label given the data point. Okay, so that is one way of understanding discriminative models. The other way is that you're essentially trying to discriminate between the classes. You're not so much interested in the data point x as it is. You assume that it's already given to you, right? You don't worry about x. You worry about modeling y given x. So one example of a discriminative model is logistic regression. What we'll now look at is a generative model. So a generative model is something that tries to model the entire data. Okay, so in probabilistic terms, it tries to model the joint likelihood. Okay, so I'm sure this will be confusing to a lot of you. So don't worry if it is confusing. Okay, so it will become clear.
Does that mean it's also looking at the probability distribution of x also?
Yeah, so x and y. So maybe I'll go to this image. So see, very crudely, right? A discriminative model, we try to draw a line. Okay, it won't worry about what the data is. All that it cares about is I need to discriminate between the two data points. But what a generative model will do is it'll worry more about the data. Okay, data in the sense
it wants to group together like similar things.
Right. I need to color this. It's not looking very good, but we can live with that. So let me try to okay, so what I'm trying to do is that okay, so what a generative model will do is that it'll try to model p of y given x. What does that mean? It'll try to say that, okay, this, crudely speaking, this particular data looks like this. Okay, so this particular data coming from class 1 looks like this. So it'll try to model the data itself, right? And the hope is that once I model the data, or once I understand the data, then that will help me classify it better, right? So a generator model, the goal is to understand the data itself, and understanding the data is the same as modeling P of X comma Y, the joint distribution, right? So remember that this comma Y is very important, right? If I leave this out, then basically these are all colorless, right? There's no point modeling the features alone. So I need to model P of X comma Y, meaning there'll be, I'll just put it this way. There'll be P of X comma Y equal to 1 for this class, and there'll be a P of X comma Y equal to 0 for this class. So I need to come up with two models, class specific models, that try to understand the data in a much better way. Okay.
So can't we take the joint distribution of
which is what we are trying to model.
Yeah. So is it fine to say that when we know very sure about the parametric form, we can do the former method? When we don't know the parametric form or the distribution, then we do the second. Because in the first case, we know the functional form. We just need to estimate the parameter theta given the data. Right? That's an easier problem to solve because I already know the probability distribution. The second case, when I don't know the distribution itself, then first I have to find the distributional form and then the respective parameters for that distribution. So that's a much harder problem.
Yeah, the second part I understand, but in the first part, right? The first part, even in logistic regression, I don't know if that is the right parametric form, right? For the data at hand. I don't know if I'm not at all worried about how the data looks like, right? So all that I'm saying is I am going to model P of Y given X in this manner.
Yeah, there you are basically, in case of logistic, you are basically talking about the hyperplane and more like a discriminating. You are interested in the hyperplane, not in the data itself.
Exactly. Yeah. Okay, so it will become clear. So we'll study more discriminative models. So for example, we'll study decision trees in week 9, which is another kind of discriminative model, but it doesn't separate the points using hyperplanes, but using rectangles, right? So as long as you understand that this P of Y given X and P of X comma Y, if you can remember this, that should be good enough. Okay, so here is one more way of understanding the generative model. That's via this generative process, right? So P of X comma Y, you can write it like this, right? I hope you all remember this particular thing, right? It's just probability 101, right? P of Y into P of X comma given Y. So how do I understand this? You can think about it this way, right? First pick a class. Okay, so let's say we pick the this red color class. Okay, so then you model the data that belongs to this class, right? So what do I mean by model the data? Let's say I model the data like this, right? So okay, so this is how I model the data. Now, why is this useful? Once I have some kind of a model for this data, I can generate new points from this data set, right? Or from this model. So how will I generate? I can randomly sample from this distribution, and I can say that one point I can generate like this. So this particular point that I came up with now was not present in my original data set. Okay, but because I was able to model this data using this curve, that gives me the power to sample new data points from this model. Do you get this point, this distinction?
Yes, sir.
Okay, so now I can sample. Once I have the model, then I can sample points from that distribution. Okay, so that is one power that generative models give you.
When you say samples, so does it mean generating new data points?
Yeah, generating new data points from the that particular model. See, now I have modeled it this way, right? So do not worry too much about the mathematical form because I also don't know. It's, let's say I have points that are uniformly distributed in this along this curve, right? Let's say that is the model that I have, and I am given these 3 data points. So once I assume this model, then I can generate more points from the model, right, which were not given to me as a part of the data set, right? So for example, I can generate this point, right? So that is the generative process in some sense. Okay, so far so good. Now, once you have learned a model for a given class, right? Say I have learned 2 models. I don't know if I can, the other model will look something like this, right? Assume that it looks something like this. Okay. Now I have learned 2 different models for these 2 classes, right? Now that is P of X given Y. I hope you're all able to see that. The model that I have is P of X given Y equal to 0 and P of X given Y equal to 1. I have 2 models. Okay. So how does this help me in classifying a new data point? That is the whole question we are trying to answer. So that is what we call a generative classifier. Does this slide make sense what we are doing here? I mean, you can stop me. If it's not clear, you can stop me at this stage.
We finally ended up doing the conditional probability, right? Here too.
Using Bayes' theorem, because we are predicting Y, and we are taking, if you take the denominator on the other side, it becomes like Bayes' theorem.
Right. So this is a good point. So what you're saying is correct, right? We end up doing P of Y given X. But the point to note is that in a discriminative model, we directly model, okay, in a discriminative classifier, we directly go ahead and model P of Y given X. Okay, we don't worry about the X at all there. Whereas in a generative classifier, we model P of X comma Y. Okay, and because we model P of X comma Y, how do I go back to P of Y given X? I use the Bayes theorem.
Okay.
Okay, so let me explain this term by term. It will become clear. See, I have a prior belief about the label, right? When you give me a data point, so you give me some, say I'm trying to classify between cats and dogs. It's a very popular example, right? So you have given me images of cats and dogs. So you give me, let's say I'm a machine and I have no idea what a cat looks like and what a dog looks like. So you give me 50 images of cats, 50 images of dogs. So I have some prior belief about the image I'm looking at, right? Or rather, even before you give me the image, what I'm going to say is 50% I know it's going to be a cat. 50% I know it's going to be a dog. So that is my prior belief. Okay, I have not yet looked at the evidence that you have provided. So that is the prior. Next, somebody shows you the evidence. So you show the machine the evidence that, you know what, this is some image that I'm going to give you, right? So that is P of X. That is what we call evidence. So the next step is I measure the likelihood of seeing this evidence based on my current belief, right? My current belief is that, let's say it's a cat. Okay, so I have already built a model of cats. So I know from my generative process, I know how cats look like. So I look at this new evidence that has come and I compare it with my cat model in some sense, right? How likely is it that this new evidence looks like a cat? That is P of X given Y. So I have these 3 terms now. Bayes theorem, what does this Bayes theorem do? It gives me a process to update my belief. Initial belief was that this was a cat, but after looking at the evidence, I am now able to update my belief about this piece of evidence that has been given to me, and that is called the posterior. Now, is
Okay,
this?
so yeah, this is quite clear. This example was good, sir. So based on whatever knowledge you have about the cat, you kind of identify that it is a dog.
Yeah. Yeah. Right. So that is where your generative model helps you. Because in a generative model, you try to understand how cats look like and how dogs look like. So by the way, this cat dog thing was actually Swarnim. This is an example that Swarnim came up with. So I am like liberally copying his example. Okay, so
from a parameter estimation point of view, instead of using a MLE estimation, you're using a Bayesian estimation.
Sorry, you're using
a Bayesian estimation, right?
Okay. I am not sure about that. So whether we are using the Bayes theorem, but we'll end up using an MLE here also. But my stats 2, I'm like quite weak when it comes to stats 2. So I will take this as a question. So are we?
So, but in the Bayesian statistics, Bayesian estimation, we end up taking the expectation of the distribution. But here we won't take the expectation. We will take the MLE.
Yeah. So this is more of MLE. So for now, please look at it as MLE because we will be doing MLE only now. But I don't want to, I can't confidently say that. I can't confidently give you an answer because, as I said, my stats 2 is.
So I think, I mean, the likelihood function in the second part is the MLE part, where you are basically taking the conditional distribution and instead of taking the raw distribution, you're taking the conditional distribution and finding the parameter by looking at the joint product of the conditional distribution given the data. So that's how you kind of do it in 2 parts. Whereas the a priori knowledge is basically whatever you had on the parameter. So in essence, when you have small data, your prior knowledge helps a lot to start with. But once you have lots of data will overwhelm, and then your a priori almost doesn't matter. It will converge in large samples.
So one question I have is, how are you getting this conditional distribution? So can you explain it with the cat dog example?
This one you're saying from where we get this?
Yes, that value.
Okay, so you're given the data, right? So you're given assume that these are cats and these are dogs. Okay, so what you're trying to do is you assume some model for the cats. Let's say you assume some model for the cat, right? So that is P of X given Y equal to cat. So it could be some distribution, right? You make an assumption of that particular distribution, and then you learn the parameters of the distribution using the data of cats, right? So you have like 100 images of cats. Okay, so first thing is you have 100 images of cats. The second thing you do is you assume distribution for cats, right? Basically, this is called a class conditional distribution, right? This is because you are conditioning on the class and you are learning a conditional distribution in some sense of how the cats will look like. That is what you're learning here, right? And then you estimate the parameters of this distribution using the data.
So again, this becomes a problem, right? So what distribution do I assume?
Agreed. Yeah. You have to. So that's a big challenge. So how do you know if it's the right distribution or not? That's a big challenge.
And when I say distribution, are we talking about Poisson and all that?
Yeah. All those fellows, Bernoulli, binomial, Poisson. So those fellows, they are the ones we are looking at.
Right.
Of course, it's a bad. The cat dog thing is a bad example for distribution because, I mean, what distribution will you use for an image? Maybe you'll use Gaussian for each pixel of the image, but yeah, in general, right? We will look at 3 distributions basically, but those distributions are the ones we are talking about. Okay, so I hope this generative part is clear. How we classify is clear. Okay, are there any questions at this stage? Okay. So yeah, so the main point of week 6, right? The main algorithm that or technique we are going to study is naive Bayes. So we are, this part is clear, right? That we are trying to learn P of X given Y, or we are modeling P of X given Y. So X is what is a feature vector. There are M features, X1 to Xm. So we have this M variables then given Y. This is what we have to model. So one crucial assumption, right, that this technique makes is the features are conditionally independent given the label. Okay, so that is what we call as naive. Right? This is a very naive assumption because in practice, you can never expect your features to be independent given the label.
Can you give us an example?
Okay, so it's tough to.
Sir, email spam you can consider, like each and every word won't be independent of.
Right. Occurrence won't be independent of each other.
Yeah.
Right.
But naive Bayes will assume that they are independent.
True. If you want an example of where they are independent, typically it doesn't happen, but we still go on and use naive Bayes. That's the problem, or that's the good part about naive Bayes, is that even though this assumption doesn't hold in practice, we still go ahead and use it. Okay, but that's, I'll take that as a question.
This is conditional independence, not IID, but conditional independence. So Y given X is independent.
X given Y, right? So class conditional independence. So example of conditional independence given the label. Okay, I'll come back to you on this. This is a good question. But yeah, so I hope all of you are clear about this step, what we are doing here. Okay, I take that as an S. Okay, so there's a very small digression here. So we have been talking about data a lot, right? Or at least initially we talked about data and then everything was abstracted out. So typically, right, in applications, we'll see data going in 3 different streams. One is text, right? Text data. The other is speech data. So speech would be audio signals, right? And then vision is basically images and videos, right? So based on the type of data you work with, ML will usually take these specific streams, right? So if you're working with text or speech data, you'll be in the area of natural language processing, right? So how do you make a machine understand text? So things like machine translation. So whatever you see Google doing, right? Do you want to translate this page into Hindi? So if a machine translation model is behind it, so some ML algorithm is being applied on text data. So that falls under the domain of NLP. And if you look at computer vision, it will be all with respect to images, right? So one example is when your Facebook images get tagged automatically, right? So how does a machine know that this is your photo, right? Or this is your friend's photo, and how does it automatically tag? It is running as some kind of face recognition algorithm on the back end, and that's a classification algorithm, or depending on the application, it could even be clustering, right? So these are all happening in the background. So I just want you to understand that even though we haven't discussed a lot about data can come in different forms. So it's not finally it's a feature matrix, but initially raw data could be in any of these verticals, or some of them I have left out here. So time series data, for example, right? So that is another type of data which I have not mentioned. So why did I digress? It is because of this. So we are trying to understand naive Bayes, and let's look at one concrete example of text classification, right? So this is spam versus ham, right? Very popular problem in, as you all know, right? So we all get spam emails, spam messages. We also get the good ones, right? which matter to us, how do we separate the two? How do we classify? So this is a typical classification problem, binary classification. The data is text. Okay, so Paul Graham, I don't know how many of you know Paul Graham? Does anyone here know who Paul Graham is?
One of the startup founders in Bay Area.
Right. So he founded a startup called, I think, Via Web very early back. I think he sold it to Yahoo, and then he then founded a company called Y Combinator, right, which is basically a startup accelerator, right? So it helps other startups in some sense, right, by funding them, by providing support and all that. So he's a very popular guy, and so he has worked a lot in spam filtering, right? Spam filtering is basically what? Text classification applied to spam data, right? So I encourage all of you to read his articles. So he has written some excellent articles in general, right? So this is on spam filters, but he has also written some other articles on life, universe, and everything, right? So it's a very good writer. So you must all go and check out some of his work. So he came up with this very nice technique of filtering spam using naive Bayes, which is what we are going to look at. Not he in particular, but he played a very important part. Okay, so are you all with me so far?
Yes, sir.
Okay, so we are trying to do text classification, right? So that's the bottom line. So far we have been looking at what? We have been looking at a feature matrix X. So feature matrix X is given to you. You have to output a label vector. So that part we all know. But what we don't know, or what we have not seen so far, is how do we convert data into features? Okay, so you are given a message. You are given this message. We offer credit card free. So this is clearly spam, but I need to teach my machine that this is spam. For that, I need features. So how do I extract features from raw data, right? So there is an entire step that we often miss out. That is called feature extraction. Okay, we'll very briefly see how feature extraction happens for text data. So can someone tell me how do I represent, how I can represent text?
Frequency of your words.
Split every word using the Python. That's split. Dot
Okay.
split.
All right.
Frequency of every word.
And then we'll have to somehow code it. Every word.
Frequency of each word. So that will be how many times each word is appearing.
Right. So remember that your feature matrix is just a bunch of numbers. So somehow text has to become numbers, right? And in that process, we also have to need to retain some information that is there in the original data, right? So as you all pointed out, one way is to capture the frequencies of the words. Okay, so this is a typical Python dictionary, right? So fee occurs once, offer occurs once, free occurs twice. So these are all frequencies of words. Okay, so this is called a bag of words approach. Okay, why do I call it a bag of words? Can someone?
It's basically a bag of all the words that is in the text.
Right, it is. You're right, right? So it's just a bag of words. You put all these words into a bag, right? This is how it will look. So what is lost in this representation? From going from this message to this dictionary, I lose some information. What information do I lose?
Sequence of words.
Exactly, right? The ordering is lost. I don't know in which order or which sequence they came. So I lose that information, but that's a trade-off, right? I'm willing to accept. Okay, so there are other representations which, try to preserve the sequence, but that's beyond the scope of this lecture. So we'll move on, right? So I go ahead and encode this as a vector, right? Remember that we want a feature vector finally. So what I'll do is I'll come up with a vocabulary of words in my data set, right? So vocabulary is nothing but go through every spam or ham message, collect all these words and form a list of such words, and I call that list V, right? That V is nothing but a vocabulary. Okay. So now you have a very clear way of encoding every message. You'll just put one or that particular frequency wherever that word occurs, and in every other place you will put a 0. Okay, so if there are n messages, I can represent each of them by a vector of size m, right? So if there are n messages, then I have a feature matrix of size n cross m. So is this part clear till now?
So can you go to the previous slide? Here, you said we'll just encode them as 1 and 0, but here we are taking 2 also.
No, right? So we'll encode them using their frequencies. Okay, it's not okay. I can encode them. You're right. So you're right. So you can encode them as 1 or 0, in which case I'll just be interested in their presence or absence, right? Presence of a word or absence of a word. But you can do slightly better by encoding their frequency. So 2 came twice. So let's say I want to add that information. So,
it's like a weighted graph, basically.
Right. Got it.
Okay. So
even here the order is not preserved. Really.
Yeah, here also the order is not preserved. You only have the presence or absence, rather the frequency of each word that is also there. But this is what a bag of words model is. Okay, so this is a good exercise for all of you to take a piece of text, and maybe you can work on that and convert it into a bag of words representation, right? So given m documents or m paragraphs or whatever, can you get hold of a feature matrix of size n cross m? So this is an exercise in feature extraction. Okay, so this is something you can all work on, basic Python, but so much has to be done before you get the X matrix, right? So before you can get hold of X, you have to do all this work. Okay, so now let's go back to naive Bayes. So what do we have to do? We have to do this, right? We have to find out, given at inference, this is what we need. If you give me a message, is it spam or not spam? So I need to find this probability of spam given message. That's what I need to do. So what do you think will be the next step?
Probability of the message, right? That's the prior.
Okay, so probability. Okay, so I'm taking a particular example. Okay, so you're right. So I use the prior, which is P of spam, and then P of message given spam. So I'm basically using the Bayes theorem, right? So far there is no naive Bayes coming in. This is still just probability only, right? So this is probability 101. P of spam given message is proportional to P of spam into P of message given spam. The denominator is the evidence part, which is like common to both classes. So I'm not interested in that. So is it clear to everyone? Can I proceed?
Yes, sir.
Okay, so now what we do is, okay, what is the next step? Can someone tell me what the next step will be? Remember that we are doing naive Bayes.
Divided by P of spam.
No, so we consider each word as independent and then.
Right, you are right. So we use the naive Bayes assumption, which is what? Each word is independent given the class, right? We are, remember that. Okay, if I have to go back, yeah. Word 1, word 2 till word m, right? There are m words in your vocabulary. So, okay, so this is what you do, right? You multiply the probabilities of all the words given the class. Okay, Okay, so we won't use all the words in the vocabulary, but here we'll use only the words that are there in your message, right? So V given spam, offer given spam, so on. Free occurs twice, so that is P of free given spam whole square, right? This is the naive Bayes assumption at work. I hope I can move on from here. Are there any questions?
This part is clear.
Okay, so the same thing you do for ham. Ham is, in case someone is wondering what ham is, it's a good message as opposed to spam, right? Spam versus ham. So this is the good class, spam is the bad class. So we do the same thing for ham. So finally we have this full form for for the Bayes theorem. So I hope you see why I left out the denominator, right? Because the denominator is same for both classes, basically the evidence part. So I just need to compare the numerators. Okay, and whichever is greater, I will say that I'll say that message is either spam or ham. For example, if P of spam given message is 0.7, then this will be 0.3. So I'll say that this message is actually a spam message. That's how I'll do the classification. Okay, so how do we? Can you repeat that? So you are given
so
a
I
message.
have one doubt here. How do we get this probability of messages given spam?
Yeah, that is I'll come. That is what I'll come to in a moment. Okay. So in case, yeah. So Himanshu, who was that who asked this part, right?
Yes, sir.
Yeah. So see, this is just Bayes theorem, right? Spam given message, you just invert it. Message given spam into P of spam divided by P of message. So P of message, I use this. If you remember, we use this law of total probability, right? And so we just expand it this way. But even if you don't remember that, it's okay, right? Just notice that the denominator is same for both, so it's not important. Okay, this is just Bayes theorem, by the way. Here we are not yet going to naive Bayes. We are just expressing this using Bayes rule. Okay, so the part that is not clear is what are these probabilities, right? What is P of spam? What is P of message given spam? So the way you do that is, so P of spam is the prior, right? So typically what we do is prior, we get it from the data, right? Let's say you have 1,000 messages in spam, 1,000 messages in ham. So what you do is you say that the prior is 0.5 for both, right? Remember that prior is something that you get by not looking at the data set, right? You just look at the distribution of messages in the two classes and you get your prior from that. Okay, that is step one. Step two is how do you get hold of individual word probabilities? So that you do this way. You look at the frequencies of the words. Okay, let's say there are 100,000 words in spam class. Across all messages, you have 100,000 words in total. 2,000 of them are free. So the probability of seeing probability of seeing the word free in the spam class is 0.02. You just do a simple division. Basic frequency-based probability estimates.
So if I say it step by step, you first see the data and you make a prediction that it is a spam. And then you go through the data and find out words which are more occurrent in the spam and get the probability of word given spam. Is that the way it processes?
Yeah. So So maybe I'll elaborate on that. So see, we need spam. We need to find out whether it's a spam message or not. So for that, I use this Bayes formula, P of message given spam, right? So this P of spam is the prior, and basically now I am at the stage of parameter estimation, right? I'm trying to estimate the parameters of my probability distributions. In the case of
that means that you've gone through the data once.
Yeah. I need to go through the data if I have to extract these probabilities. So P of spam.
Data isn't just the labels, right? In this case.
For the prior, only the labels, right? For only the prior, you only need to look at the label. for this, you need to look at the individual word distributions, right? So this,
right.
Let's say there are only these two words. So I need to estimate two probabilities. What is the probability of word 1 given spam, word 2 given spam? There, what I say is, so P of word 1 given spam is this fraction. Look at frequency of word 1 in spam and then divide it by total number of words in spam. Right? So that is how I estimate individual word probabilities. So these are essentially what parameters of your distribution. We'll come to.
So in this, I have one doubt, sir.
Yeah.
If we get a word suppose we are trying to find the probability of a spam or a ham message, and I get a word which is not there, and so the probability will come to 0, then the whole thing becomes 0 because you're multiplying by 0.
Good point. Yeah. So that is what we are going to do next, right? So let's say you get this word, this message, eat dosa, and I want to find out whether it's spam or not. And as you said, this probability of dosa given spam is 0 because there are no words, there is no occurrence of dosa in the set of spam messages I have.
Right.
Okay. So what do we do in this case? Every message that has dosa will have 0 probability, right? Now, practically, when will this happen? This will happen if, let's say, I've trained a spam filter for, say some IT application, some IT workspace, right? So you have built it for, let's say, Facebook employees, right? Now, Facebook employees in the US, right? And if you adopt the same spam filter for, say, Facebook employees who are in India, let's say some part of South India, then this will fail because if some new restaurant opens and they have this kind of, they are popularizing their dosa varieties, then that will not get classified as spam. Okay, so this is a very practical situation that you will encounter. So what do you do in this case? You do something called smoothing. Okay, so smoothing is this. So earlier you had this formula, right, for estimating the parameters: word given spam, number of occurrences of dosa divided by total number of spam words. Now what you're doing is, for every word in your vocabulary, you are giving a pseudo count of 1, right? Whether it's there or not, you are saying that add 1 to it. So make the count of that word 1. So if you have m words in your vocabulary, your actual count or your pseudo count will now become n plus m. And this will become n dosa plus 1, right? So even if n dosa is 0, I'll have some non-zero probability for dosa, right? So this
why
is
do you
how,
add that m in the denominator? One, I understand, but why is that m required?
So we do this uniformly for all the words in your vocabulary, right? So you add the pseudo count
Okay.
for every word. So there are m words in your vocabulary, so n plus m.
Okay, yeah, got it.
Okay, so this is called Laplace smoothing. There are other forms of smoothing which we don't need to worry about, right? So this basic idea, if it's there, it's enough. Okay, so this is what naive Bayes actually is, right, from a high level perspective. But so far, all this is just a good heuristic, right? So recall that we have not used distributions anywhere, right? So if you remember, what we started off with was assume some form for the joint distribution of P of x comma y, right? That is what we started off with. Generative models means you are trying to model P of x comma y. So where have we done that? Maybe we have done that implicitly, but I can't see, right? So I'm not able to. I mean, if you're a mathematician or a statistician, you will cringe when you look at this, right? Because this is what you can do this with 12th class probability, right? Or stats 1, whatever you learn with stats 1, you can do this. Very, very intuitive, but as a mathematician, I need to be convinced that this is correct, right? So how do we do that? That is the next part of the session, but I think we are already late. So only 8 more minutes are remaining. I don't want to hurry this up because there is some heavy duty mathematics coming up. Right. So
when will be the next class, sir?
I'm hoping 8 to 10 on Wednesday. Will that work for all of you, or do you have other sessions?
This is good stuff, sir. We definitely want to understand it in detail, even if it takes time.
Sure. Okay. So 8 to 10 works for everyone, at least those who are here.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir. Yes.
Yes, sir.
Yeah, if you can go through the videos, we can go through 2 hours of session, no problem.
Right.
This is thank you, sir. This was very, very helpful.
Very helpful.
Yeah. Thanks a lot. So maybe in the 5 minutes that are remaining, what I want to do is so what problems do you all face with the, so these are all, I won't call them doubts, these are all some theory questions that we need to address. So okay, so programming, what do we need to discuss? We were talking about conducting one session, having one session for programming. So what all problems do you all face and what is not clear? Can you all tell me?
So one thing is regarding the graph, that is actually not, a brief kind of class kind of for how to, basically how can we draw and that learning curves and.
Okay. So basically plotting, right? So plotting using, I'll just plotting. So there are two things, right? One is loss curve and then decision boundary, right? I think
in plotting, I would suggest, there are every time there is a plot shown in the videos, there are multiple kinds of parameters which are given while plotting. So what do all those do? What changes do they bring?
Okay.
Sir, I'm having
yeah, please go on.
A problem with the very basics of NumPy also, because the very, very basics I understand, but things like, there are various ways to reshape it. Why do we, the simple reshaping I understand, but sometimes, some of the questions are very confusing in reshaping. I don't understand why. And why do we need to, in certain cases, certain codes, we are reshaping. I don't understand why do we need to reshape in that.
Okay.
Then broadcast is another NumPy, the thing I'm clear the basics, but once it gets a little deep, I'm not clear then.
Okay, so reshape, broadcasting. Okay, so yeah.
Sir, one thing I face is when we're writing classes, like how to organize code better when we're like writing such big codes for models.
Classes also, if you could go through that in case we have time. So, we had a run through in Python, but that was, it wasn't very clear at that time.
Okay.
If you have, can we have something about the unit test part which we did? I'm not sure why we write a class for that and etc.
When did we do unit tests?
In the least square and all, each function we unit tested.
Oh, okay. Actually, please ignore that, because see, that can get too confusing. Don't worry about that, right? So
the unit test, I believe, were in MLP, not MLT.
Oh, is it in MLP?
Yeah.
Oh, sorry, I'm confused. Sorry.
No, MLT also
even
we
in
have
MLT,
some weeks.
there is
MLT also we have unit test.
Did it? Okay, I don't remember.
Regression models had it, yeah.
No, it was not MLP. MLT only.
Is it?
Okay. MLT also it is there. It is there in MLT as well.
But it's pretty basic unit test in the sense that it's just kind of checking the function. That's the
individual
functions.
That I understand, but like we did it in a specific way. We wrote a class for that, and then called a unit test dot something. I don't understand the need for doing that.
Okay, so I also don't. Honestly, I have not written unit tests for any of these things, so I don't even know how they work. So I am the wrong person to ask. Maybe you should ask Abhishek from Mad1 to help with this. Meaning, really, that will be the right thing to do, because see, this is more. See, honestly, you can write all this code without using classes. That's the first step. I mean, the first clarification that I would like to give is that classes are not absolutely necessary when you're learning to code these techniques. Okay, so don't worry too much about the classes part, but still, classes can be useful to useful in certain cases. So see, where they'll be useful, I can tell you. sklearn, right? If you look at how many of you here are doing MLP also along with MLT?
I am.
Yeah, most of
I am
us
doing
are,
it,
sir.
Okay, so if you look at sklearn's most of sklearn's functions or APIs, they have two things in common, right? They all do a predict, they all do a fit. Okay, so these are like two methods which are common for all sklearn models. You fit on some data and then you predict on some X test, right? So in MLT, what we are doing is, I can only talk about it from the MLT point of view. We are writing classes in such a way that they mimic your sklearn's APIs. Okay, so that is basically what we are trying to do. So any class that you write in MLT, say if you write a linear regression class, the hope is that you have one method which fits your data. Okay, this will be one method, and you have one method which predicts, returns the predictions, right? So this is what at a very high level, this is what we want to achieve in MLT by writing classes. Okay, now the question is, what if you have these two methods that are enough? Now, why are you writing all these other methods? Basically, they are needed for fit and predict. So for example, if your linear regression would require you to, when you're fitting the data, you need to compute the linear combination. So I can just for the sake of adding something, I can add I can add a linear combination just so that I make my life difficult. I can do something like this, right? And I can do return sorry, this requires what? W and X, right? XW, basically what we are looking at. So this is, you do this so that your code becomes modular and all that, but if you want to answer 0 and 3 together, then the basic idea is you want to mimic sklearn APIs from in MLT using only NumPy.
So in this return, will we use self.x?
Yeah. So correct. So see, all these things will now start coming in. So you want
self, right?
That was week 11 or 12 of Python. Very quickly done.
Yeah. So you want these to be your you can do all this, right? So and then so the basic idea is you want your classes to mimic the APIs of sklearn, and the most important APIs are fit and predict, and these are in some sense the main methods that you write in your class. The other methods are more or less like helper methods which help you fit and which help you predict. Okay, this is one way to organize your code better, and this is one reason why we are using classes.
I think it's a very good idea you're doing this, because from an industry point of view, I think these skills are very useful, even the unit test and classes.
True, I agree, right? So see that, yeah, I agree with you completely, but the only problem is that the question is, I must not let classes, the idea of classes should not prevent me from understanding the technique better, right? So what is happening is with some of us, right? I'll put it this way: some of us are getting consumed in understanding the Python aspects of MLT rather than the actual technique, right? So that is the problem we need to solve somehow. But yeah, I agree with you that these are, from the industry standpoint, this is very useful. Okay, we'll try to work on this.
Sir, and one last thing, sir. I don't know if anyone will agree with me. Like the questions that we see in the programming assignments, the questions are a bit ambiguous, sir. So if you can take a note on that also, that would be really helpful.
So
Okay.
even text formatting, like please try to improve that, because it formats like till the, we have to scroll to read each and every question. Like,
right, agreed. So see, I think partly we are trying to fix it. So will something like this work? So for example,
so that is okay, like, but let's say in week 5 I have seen a programming GPA where it says to use L2 regression. Now L2 regression is ridge regression, correct, sir?
Correct.
And ridge regression formula is that lambda into W transpose W.
Correct.
So I was using that, and the programming was constantly giving me wrong. Something problem, test error not complete or error. Okay. So now after that I went to use L1 regression, that is lasso regression, and the program ran clearly, means properly, sir.
Oh, you're talking about this
Yes,
week,
sir.
this one?
Yes, sir. Yes, sir.
Okay, see, I think, okay, focus on this part, right? I think you are missing out on this part. I hope you get it. So read the question again. See, this is, in this case, it's not a problem with the question. You have to read the question carefully, right?
So it's not the loss, it's the gradient. That is what you're trying to say. Sir.
Yeah. Right.
So also here, if you give the outputs, in a proper way, then probably
Correct,
we'll be able to understand the question better, I feel.
Yeah, I agree. Totally agree. So see, something like this will work, right? If you take up, I'll just show you week 6 what we have done. Okay, don't worry about what these things are, but just look at the form of the. So will this work? If your function has this kind of a description. So you have to basically estimate something, and you are expected to return a dictionary whose key is an integer, value is a numpy array. Will that work for every question if we have something like this?
Yeah, I think it should be okay. It is better than the number one that we see generally.
Oh, you're talking about this expected output, huh?
Yeah, yes. The expected output is a vague number, and then we can't make out what exactly is the output required. So sometimes the questions, as Abhishek said, it is ambiguous, and then if you see the output, we can kind of make out what is expected of us to do.
Okay, so this is, yeah, I get your point. I agree, but I don't know how we are going to solve this problem, right? This requires some.
Because while we were doing Python, we used to see the expected output there.
Yeah, there it was easier for us to configure.
Okay.
Here we don't know how to see here in Python, if you remember, all of the answers were integers, right? Or integers or strings.
Strings, yeah.
Here the answers are, first, they are probabilistic in nature. So you sometimes you don't expect the answer to be exactly what we have in mind. So it's some numpy array, right? And this numpy array need not be exactly accurate. I mean, the same values it need not have.
Yeah. Yes, sir.
Okay, so that is something we are yet to figure out, how to test your code properly and display the correct things. We have not yet figured out.
Yeah, sorry. In some cases, you do give expected output and students output or something like that. In some problems, we have that.
No, in fact, in every problem we have that, right? So, for example, if I, let's say I am supposed to return one, I'll just take this example. You are supposed to return NumPy array of size 200. Okay, so let's say I return a set of, I just return zeros. Okay, now if I test run this, so you get this expected output and you also get the student output.
Yeah.
Oh, we don't give you the student output.
You do in some cases.
Student output is this, but the expected output is not given, right?
EOP
Just
is the
one.
expected output. SOP is the
Expected output is also given.
No, it's just one.
No. I meant like in the actual output, right? You see EOP. So this EOP is expected output.
Oh.
Okay, so you guys don't know this, is it? Maybe we have to put one announcement. Yeah, this
But
can
sir,
be.
even that works only when our code is running error free. I mean, if there is some error, that wouldn't come up.
Yeah, but then you would have passed the test case, right?
Actually, error messages come up. I think that is
the
okay.
np.zeros. The same case.
Yeah.
Can you try without this return np.zeros?
Then I hope you will get an error message rather than. I don't know what will come up, but let's see. I still get an error message. Sorry, I get this EOP. See, there are two things, right? If
sir, actually SOP is there.
SOP is also given
there. Also there. Yes, yes.
Oh, is it?
Yeah, in the last.
Oh, okay. Yeah. So see, so one way to parse this is you can copy this. Yeah, you can copy this and paste it here and see what happens. But yeah, I get it. I mean, even if we give you this, it's very tough to parse this.
Sir, until now, I didn't know this existed. I just went by looking if it passes or not.
Okay. So from now, please note this. I think for most problems, we will give you this EOP and SOP. EOP means expected output. SOP means student output.
I used to print and see. That's all. Every time.
Right. So if your code has an error, right, something like let's say some exception, then you will not get this. I think you will get a proper error message.
You'll just get the error, yeah.
Right. So, okay, you get the. Anyway, so we'll see what can be done, but unfortunately, he mostly will have to stick with this interface, whatever you've got. Okay, so we'll meet at we'll meet on Wednesday 8 to 10. That's fine, right? All of you?
Yes, sir.
Okay.
Sir, it's AM or PM?
PM is
PM,
fine,
okay.
right?
Yeah, it's fine.
Okay, then we'll continue from where we left off.
It was really a nice session, sir. Thank you. Last week also I attended. It was like more into what we want, this kind of sessions. It's very thankful.
It clears our concepts, sir, rather than only the activity questions, practice questions. I mean, this is better.
Yeah, exactly.
Sure. We'll try to replicate this for all the weeks moving forward to the extent possible. Okay, yeah. Thanks, everyone.
Thank you so much.
Again, yeah.